time we start. My name is Lars Nordström. I will be chairing today's PhD defense. Before continuing, I would like to remind you that there are emergency exits, one in the aft of the room and one here up at the front, and there's restrooms just outside that door. With that said, I also want to inform you that we will be recording today's event. So if you disagree to being recorded, there are exits at the aft and the front of the room. So welcome everyone, and specifically welcome to Niclas Johannesson, who will be today defending his PhD thesis entitled Multi-Terminal HVDC Protections Based on Transient Line Modeling. I will be introducing shortly what will happen, but before doing so, I would like to introduce the other main actors of this event. So in addition to Niclas, we have our faculty opponent, Professor Beerten from KU Leuven in Belgium. We have a grading committee consisting of Dr. Engineer Anne-Katrin Marten from 50 Hertz in Berlin, Germany. We have Professor Stephen Finney from the University of Edinburgh. And finally, we have Professor Bollen from Luleå Technical University. Also important for taking us to this day are the supervisors. Niclas is Associate Professor Staffan Norrga, seated over there, and Professor Hans-Peter in the back. So these, and of course also the audience in the room and online, are all important actors, as you will see during the proceedings today. This is what we will be doing. My main responsibility is the first bullet, opening and introducing the day, which I'm doing right now. After that, I will hand over briefly to Niclas to make any announcement if there's any corrections or omissions or little errors that he wants to point to in the thesis. After which he can then continue to present his work, focusing on contributions, and it's going to be a presentation of, I guess, around 30 minutes or so. So that's 8 years compressed into 30 minutes. After that, I will be inviting the faculty opponent up here, and Niclas and Jeff will be discussing the thesis, finding, I'm sure, strengths and weaknesses and other perspectives and novelties in the work. Once that's completed, it may be that we should allow ourselves a short break to stretch our legs. I'm expecting that we will have spent an hour and a half or so when we're at that point. After that, we will then be passing the word to the grading committee, who will be asking any complementary questions or clarification matters that they would like, in addition, of course, to what we've heard earlier, where Jeff and Niclas discussed the thesis. Finally, once the grading committee have exhausted all their questions, the floor is open for the audience in the room and online, and we will be working with the technology to get that functional. Oh, now the online staff people can see me too. Finally, once we're all out the questions, the public part of this defense is closed, and the grading committee will convene in a separate room to discuss whether the work is acceptable as a PhD thesis or not. And then after that, we will reconvene in the lunchroom, or will people be staying here? Okay, so once we're done here, you're all welcome down to the lunchroom to wait for the announcement from the grading committee. So that's what's going to be happening, and I will be here to guide us through the process. And as I mentioned, it could be that we put a break in there between the discussion between the opponent and respondent and the grading committee, just to stretch our legs. So that means we can now move on to the second item. Niclas, are there any corrections or errata that you would like to maybe made public before the discussion?
Not that I know of.
Ah, very good. Brave man. So with that, I will be stopping my screen sharing and you can pick up yours. Mm-hmm. And then I'll hand it to you to present your work.
Okay. Mhm. Okay, yeah, I think that's it. So for those who don't know me, I'm Niclas. I've been working in Hitachi Energy for the last 12 years, 8 of which I've spent partly working on this thesis. That being said, I should clarify that these are my opinions and yeah, not necessarily those of my employer. Yeah, I've tried to follow the same kind of layout as the thesis itself, starting with some introduction of HVDC, I guess mainly for family and friends that after 12 years, finally, they might understand what I work with. Then going into more of the research question, moving on to some transmission lines and traveling wave theory, and then starting with the publications one by one, more or less. So the power system is basically based on alternating current, so AC. So both generation and consumers are AC. And I mean, so far it has been working fine. However, now with the renewables coming in, we're shutting down nuclear and coal and replacing them with wind power. That means that we have a problem in the AC network, basically, because instead of having generation where people live, then we kind of replace it with generation somewhere else. And this change is fairly quick, considering that the AC network has been built over 100 years. So in addition to this, we also have the variability of renewables, basically. They are not always 100% operational, depending on the wind conditions, of course, which means that in order to handle this without shutting everything down a couple of times, then we need to be able to increase the trading, and we need more long distance transmission. And these two are very much the perfect applications of HVDC, which has the benefit that transmission using DC does not generate any reactive components, which means that you can basically transmit over cables for a very long distance and also over headlines. With AC, you cannot really, I guess you could technically, but you need some compensation. And especially for submarine cables, that is not really feasible, because then you need to bring up the cable and then put in a reactor, and then so DC is much better in that case. However, the drawback of HVDC is that you need the conversion, and that is where the cost comes in. I've tried to use, or I did a lot of figures also that I kind of cut out of my thesis. So here I got to use one of them. So I figured I would show some pictures. So this is the NordLink cable. So it's 525 kV, 1400 megawatts. 1400 is about, I think, this area number 4 in Sweden. I think it's between 2 and 3 gigawatts. So it's basically half coming in through 2 of these kind of size cables. Someone has also been clever and writing positive and negative. It's one way to keep track of them, I guess. Yeah, so this is how a converter station could look like. Some of them are also a little bit fancier, I would say, with some curves and, you know, maybe sometimes some grass on the roof. And this is more of a functional, maybe. Architectural style, agricultural, maybe. But they're fairly big, and as you can see, they are mostly buildings, so you don't really see much. You see in the bottom part of the figure, you have the AC side. And then these big green boxes in the middle are the transformers, or they're actually sound enclosures of the transformers. Then going in, you have the wall bushings into the reactor hall. And then you have the valve hall behind it, which is a little bit lower building. And then finally the DC hall. Yeah, and you can also see someone has parked a car. So for reference in terms of size. So this is one picture from inside the DC hall of NordLink, or one of them. Also, just for size, so this is how 500 kV HVDC equipment look like. In the front, you have the cable termination. So this is where the cable comes up from the ground, transitioning into the DC bus bar. You also have the voltage divider, which is also kind of important later on for the protections. And to the left, you have a big resistor, actually, that is the discharge resistor. Since this is a rigid bipole, you can, in case you get the fault in one pole, you can reconnect the cables, so you get monopole operation. You also have some high-speed switches in there as well, some disconnectors. Yeah. So today, most of the HVDCs being built are point-to-point, meaning that you have one converter that converts from AC to DC, and then another one DC to AC, or depending on the load flow. However, when we are kind of moving on to more and more of these in the network, then there might be some opportunity for optimization, basically. Maybe I should say also that some of you might think that this is Europe, but it's not really. I've taken some artistic liberties of moving the coast to make it look nicer, mainly because I wanted to fit the one that is kind of based on IFA 2 on the left side, which is, I guess, my favorite HVDC project, if I got to pick one. So this is the motivation for multi-terminal HVDC. So to the left here, you have one situation where you have wind farms offshore, and then you have HVDC connecting it to the coast. In this case, you can use them fully only when the wind is at full power, basically. So instead, if you go to multi-terminal configuration, during days when the wind is not at full power, then you can use the onshore converters and the cables to also exchange energy between these two networks. Another benefit or potential optimization is that this is what I like to call the German example. So to the left, you have a wind farm connecting to the onshore network, but the high load areas are to the right, some big city, which means that in order to transmit the power down to the cities, you need to build an additional link. So in this case, in case there is not, let's call it big demand on the coast, then you can basically remove one converter, and then I have a 3-terminal instead. In addition, in case the wind or the power is flowing from the wind farms to the city, in this case, instead of converting it from AC to DC, DC to AC, AC to DC, DC to AC, then you only have 2 conversions. So AC to DC and DC to AC. So you will also reduce the losses. So this is a picture kind of showing how to handle faults in point-to-point networks. When you have only 2 converters, then in case you get a fault, then you can trip, then they trip both of them, basically. And then you can use the AC breaker on the AC side. However, if we start connecting them into a multi-terminal system, if you get a DC fault, basically all of the converter is going to contribute with the fault current, which means that in that case, you would need to trip all the AC breakers of all the converters. This, of course, might be acceptable for these kind of small examples I had before, but with this one, it will for sure not be a good way. If each of the converters here at the bottom part is 1 gigawatt, for instance, then it could lose 6 gigawatts in case of a single failure, which is more than most networks could handle. I think maybe only China or something. So that is why we need DC breakers, basically, which is fairly new, I would say. Research is definitely ongoing. But in case you have a DC breaker, then you can split up the system into multiple sections, meaning that in case you get a fault on one, you disconnect only that one and not all of them. So in case you get a fault in this red one, for instance, and the green and blue ones can continue in their operation. In that case, you would lose only 3 converters. Of course, after the fault, you can do some reconnection and then start up again. So that leads to the research problem, I guess. I think in the instruction it said that I should formulate it. So I tried to do it by this yellow box with a question mark in it. So basically the research question is how to, if you have DC breakers in a DC network, when do you trip, basically? When do you decide that the breaker should open? In this example, where we have DC breakers pretty much everywhere on all the lines, then you should operate during these 2 internal red ones. However, the green ones are external, meaning that they should be cleared by different breakers, which translates that the line protection on the left side should not operate, basically. So that is the selectivity part, basically. In addition to AC, or in, I would say, yeah, in DC, if you get a DC fault, basically the transients are very quick. In AC, I mean, I guess the drawback of AC in terms of cables and such is that you get the reactive components, but in fault cases, it actually helps you. So in DC, everything will kind of contribute immediately, which means that even you get a fault in one part of the system, it's going to be all the parts of the system going to see it very quickly. Whereas in AC, fault in France does not necessarily cause a big disturbance in Germany. Then we come to the, I guess, the most difficult question, I would say, reliability, which you can divide into dependability and security. Dependability is that the protection is able to detect the fault. It also means that the protection should operate also during kind of strange scenarios that you could not even think of, basically. Everything has happened, everything has gone wrong, but it should still operate. Then you have the opposite, which would be security, that even if you get some strange disturbance, the protection should not operate in that case. The problem is that these are kind of very difficult to evaluate, which I think is probably the most troublesome, let's put it like that, for making research. Because the only way to actually evaluate them is basically having them in operation for 30 years, and then you can look at the statistics. So these two are kind of important to always kind of keep in the back of your mind. Because if you try to optimize for something, then you will always kind of end up doing something else or making something else worse. So in case, I don't know, you put some logic in maybe to block the protection, etc. Sure, I mean, you're going to increase the security, but dependability could also be sacrificed, because that the same logic could basically prevent the protection from actually operating when it should. Yes, so this is basically the foundation of this entire work. all lines, I would say, both overhead lines and cables, have distributed parameters, meaning that the capacitance and inductance are not lumped in one, but each kind of unit of length has both. That kind of gives you a set of differential equations, which gives you the traveling wave equations, where you have basically the one that kind of determines on voltage, how voltages and currents behave, are the propagation constant and also characteristic impedance. So instead of going too deep into the mathematics, which I kind of do in the thesis, I guess, I prepared an animation that will kind of show you what these equations mean. So in this example, we have a fault on the left side, which causes a disturbance. So you see the current is starting to increase here on the left side. And then the wave is kind of propagating towards the other side, where you get the reflection. You see at time 5 in this case, you open a breaker, which forces the current going down to 0 again. And even though the current is 0 at one side, it is not 0 at the other side, because you have reflections going back and forth. So, in summary, what it means, or these equations mean, is that the relation between a wave entering a transformation line on one side and the other one is the what I call H. So it's the propagation function of that line section. And then you have the positive wave, which is always going from the sending end to the receiving end, and then the negative wave going in the opposite direction. And what defines this sending and receiving end is the direction of current. So in this case, it's from left to right. So how this is going to be shown is basically that you have a time delay. And then also attenuation. So whatever you do on one side is not going to show up on the other side until some time later. And when it eventually shows up, you're going to have some kind of propagation attenuation. So you're going to have a little bit of a smoother wave coming from the other side. So this is very much central for all these kind of protections. So I guess there are two ways of doing this. Either you base it only on local measurements, or you can rely on telecommunication. In this case, it's only using local measurements, which means that somehow the protection on the left side here needs to be able to differentiate between this remote internal fault F2, and then it has to differentiate between that one and the two external ones. Luckily, in this case, we have a reactor between them, meaning that there is some kind of hope to be able to see slightly different responses from them. However, since it's a reactor, then it means also that the difference is only going to be transient. So it's not going to be a steady state difference, which means that you need to detect this at the very first instant when you receive the wave. Since the voltage and currents are always the sum of two waves, if you want to detect this kind of internal fault, you need to be able to differentiate something happening in the backward direction from the forward direction. And what I proposed in this paper was basically to use the incident wave. So basically you eliminate one of the waves. So you only see the one that is coming from the line into the terminal. This is done by combining voltages and current together with a characteristic admittance in this case, which in the time domain translates to a convolution. And this kind of describes the last part of the title, I guess, based on transient line modeling, because how it's used or how I implement this is based on the universal line model, which basically says that if you calculate all the parameters in the frequency domain for each frequency, these are these points, then you can find some approximation, basically, which allows you to implement them in the time domain very quickly. Yes. So using that then we can calculate the wave. However, since I said that the difference between internal and external fault is only going to be transient, then in order to actually detect something, then you calculate the slope of the wavefront, basically, saying that a fault beyond this reactor on the remote side will have a slower wavefront than the internal one. So in order to test this, I put together some simulations, and also in a multi-terminal network, you will always have some kind of flexibility, I guess. So you can always have different configurations. So then I tried here to disconnect one of the converters, basically, then simulating internal and external faults, because ideally we don't want to have different kind of behaviors of the protections, and that also comes back to this dependability. So these are the simulation results. We have a DC voltage and current. So the solid lines are case 1. It's when all the converters are connected, and then the dashed ones are when you disconnect converter 1. And you can see voltages and currents are both slightly different. Voltage is almost the same. But if you calculate the waves on this, you will see that they are exactly the same. So this means that if you're using this traveling wave protection and then actually extract the incident wave instead of the sum of them, you are independent of whatever configuration you have in the backward direction, so to say. Then I also compared it a little bit to some other proposed protections. You have a voltage derivative, current derivative, and then a protection based on the product of the two. And you can see all of them are kind of small variations. Voltage derivative does not change very much. That's because of the reactor. So you will kind of always get a very strict reflection. But again, using the traveling wave, you get identical results. Okay, moving on to the other way of doing things, which is kind of, I guess, what I've tried to focus on, using telecommunication for the detection, basically. And the advantage of doing this is that you don't need this kind of coordination of setting, but you can make a protection that uses information from both sides, basically. So then it's much easier to differentiate between these external faults. And in order to do this, of course, we need as fast as possible telecommunication, which is possible using an optical fiber. So then it's more or less a dedicated one. I should say that this is not really how communication is working today, but it's possible if we need it, I would say. So just as an example, a cable of 300 kilometers could give you a time delay of 2 milliseconds. Then the question is, how does this 2 milliseconds affect the performance? So the first protection that comes to mind is always the differential protection, which I guess it's kind of a saying in the protection business that if you can, you should always use a differential protection. So you basically calculate the sum of the currents, which should equal 0 unless there's an internal fault. The problem is that when you apply this for transmission lines, the traveling waves will not make sure, they will generally not be equal during transients, which I've illustrated here in this example. That makes them a little bit sensitive. So in order to overcome this, they are typically, I mean, in existing HVDC protection systems, they are kind of slow. So hundreds of milliseconds, so which is way too long for multi-terminal protection. There has also been some proposals on introducing some blocking scheme, because basically you can look at the polarity of the difference between the currents. Because an external fault in the backward direction in this case will have the opposite sign. The problem is that then again, you actually increase the security of protection, but then you reduce the dependability, because then you can actually block the protection during an internal fault. So instead, as I said, that this relation between the wave entering the line on one side is the propagation function. Then you can actually use that for basing your protection on, rather than only the currents. So at the bottom you also have the waves from this example that I showed before, or this animated. So on the left side you have the positive wave. So yeah, it starts at 2 milliseconds when the fault applies, and then it arrives on the other side a little bit later. So translating this into a protection would mean that you calculate the wave on the sending end, and then you calculate the wave at the receiving end. And by applying the propagation function to the sending end, you will kind of estimate the wave that will kind of arrive at the other side. And by calculating the difference, you will get this ITV def, which should be 0 always for all conditions, as long as the transmission line equations are fulfilled. So we know that it's stable during external faults. Then the question would be, what can we expect during an internal fault? Which you can calculate by kind of considering it as, or your transmission line of L, you can consider it as 2 pieces, basically. Each one kind of fulfills the transmission line equations. Doing that, you will see that during this case, you would get the differential current would be this HB times the fault current. So this is propagation function of the line section between the fault and the receiving end, meaning that if the fault would be exactly at the remote or the receiving end, then this HB would be identity matrix, and then you would actually see exactly the fault current. So coming back on how to do these calculations, then we use the same approach as for the first one, basically. The difference here is that here you also have the propagation function, which in addition to this rational approximation, then you also have a time delay. There's also some optimization you can do here. So if you extract the minimum time delay, which is the largest common delay that you can have in the propagation function. Then you can actually remove this one, saying that the traveling wave differential current is actually calculated by the sending end sometime earlier, basically. So the sending end is always happening before the receiving end. And this helps out in the implementation, because that means that you can subtract this from your telecommunication delay. So even if you have a 2 millisecond time delay between sending and receiving end, the protection is not going to be that slow, because you can subtract this one. So again, this very nice 4-terminal circuit, courtesy of Leuven, I guess. So here I simulated an external fault. I guess voltage and current are not that interesting, but to the bottom right here, you have the blue one is the wave on the sending end. So this is the wave that immediately when the fault happens, you can kind of see it's entering the line. The red one is by applying the distortion to the wave that you calculated. And the green one is the wave that you measure on the receiving end. As you can see, the red and green one are more or less identical with the time, except for this time shift. And then calculating the difference between them, you can see it's strictly 0. So, and I guess the background of this paper is that I had one paper and then it was rejected later on, basically saying that communication is always too slow. So that's why I try to kind of face that. Okay, what is the performance we can expect if we do this kind of special optimal or optical fiber communication? So then I compare 3 different methods. First of all, you have the overreach protection, which basically means that both sides will always need to detect the fault. And if both sides confirm that the fault is in forward direction, then you trip. Then we have the normal differential protection. Here we assume that this kind of sensitivity to external faults is kind of fixed. So we have solved this somehow. And as you can see in the normal differential protection, you need to compensate for the telecommunication, since you always want to compare the current that was measured at the same instant on both sides. Before the current on one side has actually been received on the other side, you will have the telecommunication, which means that you need to delay the calculation always by the same amount. And then finally comparing it to this traveling wave differential protection, which you can see it looks much worse than it is maybe. So this I have shown how to do it in both directions, basically. And you can also see that you only need to calculate the characteristic impedance once. So this is basically the wave propagation and the communication path during an internal fault. So you can see you have a fault fairly close to the terminal B, which launches waves going to both directions, arriving at tau B and tau A. So the detection time in this case would be that, first of all, the protection needs to detect it at B, then it needs to be detected at A, and that detection from A needs to go to B, basically. So you get a very long time delay. However, in the opposite direction, if you have a fault which is very far from you, then you can see that you get a much smaller time delay. So similarly for differential protection, So here this dashed line is the reference, basically. So the current at side B should be compared to the current at the same time on A. Yeah. Whereas for the traveling wave, you actually have the inherent time shift of this tau min is basically that sending end is always lagging, which means that it's already in the progress of being sent over the telecommunication, which means that you actually get a very small time delay in comparison to the full telecommunication delay. So plotting them looks kind of like this. So you have, in general, I would say, a dependency on where the fault is, on how long it's going to take to detect it. But I guess the conclusion is that it is possible, even if you have a 2 millisecond delay, it's still possible to detect it faster. Yes. Then the final parts, which are kind of, I will just go through them very quickly. But basically, the idea is to, because we are using these protections, we rely very much on the internal representation of the line. So it requires you to know exactly the characteristic admittance and propagation function. So the question is, what happens if you don't know them perfectly? And that will result in a false differential protection or differential current during external faults. So what I did here was basically to try putting small differences in each parameter to see which ones were actually the critical ones. Yeah, so the result from this was basically that the length is the most important one. Also, you can see from this figure is that this is because of the time delay. So these are basically what the differential currents looks like. Played some with the animations. And the reason for this, if you look on the two waves that you are actually comparing, you can kind of see that it's because you have this small difference in timing, basically. However, it's not the full truth, so to say, because even if you would compensate fully, then you would still have some kind of difference in attenuation. Which kind of brings us, I guess, to the final paper. So since we have kind of discovered that synchronization of the waves is very important, then I thought about it, how to kind of solve it. So basically, this is an illustration of what happens if you have a delay error. So everything is perfectly fine. The signals are identical, except for this time difference. And if you plot this, so this is the compensation delay that you would need to basically wait before you perform the calculation. So this is while you wait for the telecommunication to arrive. So in this case, if you have an error, then the nominal time delay will kind of cause some differential current, which is not zero. Whereas if you find the optimal compensation delay, everything is smooth sailing. And the idea behind using this is saying that if the waves are identical except for a time delay, then the question is how to find that time delay. So this is just an example of when both are kind of saved in some kind of memory. And then you can see that if we shift the green one a little bit further, then we would see that they align perfectly and you would get zero differential current. So in order to do this, which also has to be done in real time, I've formulated some kind of relaxed objective function, which allows you to, instead of finding the optimum, you can kind of find something that you think might be of the optimum, which means that you can perform this in predictable time. So the final time we see the same picture, I guess. So to simulate this, I tried to introduce an error both in the telecommunication and also in the cable. So this is the result. So on the left side, you have the differential current, basically. So without doing anything, you get 3.75 kiloamp volts differential current. If you were to eliminate the telecommunication error, which you would do in case you have a GPS or some kind of time synchronization, then you would reduce it to 0.45. Whereas when you're using this kind of method to dynamically adapt your compensation delay, you can reduce it to 0.18. And of course, the reason for not getting this kind of perfect zero current is that since we decrease the length, we also have some difference in attenuation, which means that there is no perfect alignment of them. So in summary, I guess, so protection design is always a trade-off between conflicting objectives. So I think there is no hope for finding an optimal design for any configuration, especially not for multi-terminal. And in order to have something, I think that telecommunication might be a much more flexible way of doing it. That you're not dependent anymore on this reactor. What we've also seen is that the traveling wave differential is also sensitive to having these parameters correctly estimated, which finally we have kind of almost solved a little bit with this final method. Yes, I think that's it.
Thank you very much, Niclas. Moving on to the next step in the proceedings, which means inviting the faculty opponent, Jeff Beerten. Will you be sitting down here, or what's the most efficient? Because we can't have Jeff sitting and you standing. That doesn't look good. Please come up here, Jeff, and then we'll figure this out. I guess you might be needing your slides and so on. I suggest that the both of you stand up. When you get exhausted, the both of you sit down.
Okay.
So please, Jeff and Niclas, take us through the thesis.
Okay.
Oh, yeah. This one, then, so that the online audience.
So yeah, Niclas, first let me thank you for the nice and very comprehensive thesis text that you presented. I think one of the main merits of, is it working?
Yeah, did I mute it there perhaps?
Okay. I think now it's working.
Yeah, thank you.
So thank you for the very nice and comprehensive thesis text. I think one of the main merits of the work is that you really show that traveling wave protection could work, that it has a lot of potential, and it's a promising way forward for DC system protection. So I really appreciated that. Now, a number of options have been proposed in the past. They weren't really brought to commercialization at that point in time. They also had their challenges. And I think a real merit of your work is that you've revisited some of those initial ideas, improved them with new insights, new modeling methods, and use them for protection. So I also think that the work will also be an inspiration for future researchers afterwards to develop new algorithms. What I also appreciate a lot is that you base yourself a lot on the theory, so it was very rigorous with mathematical detail. So I appreciated reading that in the text, and I think that using the ULM in a reverse way, let's say, to put it in a protection device is definitely something that is novel and will also inspire others. Now I understood that as an opponent, I'm supposed to oppose some of the things in the thesis here as well, and that I could see it a bit as a friendly boxing match. So some of the things I will put forward to you might be a bit provocative.
Okay.
They're meant to be a bit provocative, I guess. So as in a boxing match, feel free to hit back at least verbally, and yeah. And in a friendly way, also do that from my side, I hope. So if we start a bit with the history of things, first discussion I would like to propose is to put things a bit into historic perspective here. So the work on traveling wave-based protection was started, I would say, in the 1970s, amongst others by a group of Japanese researchers. Tagaki produced a number of ideas on it. Which is also described in the PhD thesis of Professor Bollen, is also present here. So the essential idea was that you define a traveling wave that is going over a line from which you derive a detection function, and you would send the information on this wave that is traveling over the line over a communication link, so you could kind of recompose the wave quantities at the other end and then compare them to what is arriving, which is a bit in line with, or quite in line with the, let's say, overall idea that you used in the thesis. Could you maybe first point out a bit or discuss a bit where you see the main differences between your work there and what has been developed earlier in terms of implementation, in terms of novelty? Where do you see your main contribution with respect to earlier work on traveling wave-based protection?
Yeah. I'm not sure if it's it sounds like it's working.
Yeah.
Okay. Still have the red light. That's why I was wondering. So basically what I've done is, I would say, updated a little bit. So in addition to using this kind of new ways of calculating the waves, it's also in the phase domain, I guess. And this paper that you referred to, Takada, actually I had a real problem finding it. But there's also a patent application, I think, in 71, which also uses very much the same thing. It actually came up when we applied for a patent on this before this work ever started. So that was a good idea because they are very hard to find. So I would say, yeah, that is the difference. And I guess it's kind of, as you said, a bit of a upgraded, so to say, with modern, because I think it's too bad that when all of this kind of work was done in the 70s, we did not really have the potential of the computers today. So yeah, I would say that is the difference, I guess.
Yeah, where I see the main upgrade in what you proposed is a frequency dependency of the parameters, and that you take into account by implementing the universal line model there. And that's something that, let's say, the initial algorithms didn't necessarily start from, or as at that point in time, well, the vector fitting hadn't been introduced. We didn't have the same efficiency in modeling in the MT tools as we have nowadays. So it's really the frequency dependency of the parameters, I would say, that is really novel to your method. And the first algorithms in the 70s and the 80s, they were mainly focusing on overhead line based systems. Do you think they could have been used in cables, taking into account where they were taking assumptions?
Yeah, maybe. I guess it depends on the length, I guess. As well, but
I would kind of disagree. I think it's the frequency dependency that is really key here, and that for cables plays quite a huge role in lower frequency ranges as well. So yeah, I think that there is probably where things would have gotten stuck a bit. But we'll get back to that point later on. Going further a bit on cables and overhead lines, you mainly looked into cables, or you looked only into cables. The earlier work was looking into overhead lines, and you point out in the thesis text where you present the equations. Well, in essence, from a mathematical point of view, it's the same equations that govern the behavior of line or things going over the line, traveling waves. But the parameters and the properties are quite different. So I would like to hear also from you a bit how those would be different in general. So you're doing a fitting and a phase domain, but if you also present going to the modal domain to describe, well, the propagation properties over the cable. If you think about the cable, you got different modes propagating over the cable. Which would you say is the key mode? Which is the one that is most important for what you're proposing?
I think that pretty much for all of them, I mean, they have kind of been grouped together, I guess, because the coupling is so weak. So they end up having pretty much only one delay. And the only time I think I saw them kind of having different delays was when I tried this changing parameters of one of them, basically. So increasing the permittivity of one cable, then you got 2 different delays. So I guess it's, yeah. Tricky question, though. Which mode? Yeah.
Well, you've got several conducting layers, right? In the cable, you got say the main the conductor. You got the screen. You have other ones as well. But I would say that for your application, there's one that is prevailing.
Yeah, but I guess if there's no coupling, I guess the 2 modes are kind of the same as.
You mean for the 2 different cables?
Yeah.
Then yeah.
Oh,
well,
okay.
Internally in the cable, I would say.
Meant like that. Okay. Yeah, that I think I have not studied.
Yeah, well, it's the one between the conductor and then the sheet, which is the main one that is important here. And going back a bit to overhead lines, there the situation is a bit more tricky. I would say, because you have a lot of conducting layers. So yeah, I think there as well. Yeah, if you would think about an overhead line there, where would you say that if you think about going to the modal domain there as well, and you see modes as let's say waves propagating through different parts of the line and the ground potentially, where do you think the most tricky part could come in terms of the modeling for an overhead line?
I guess it's always the ground mode, I guess.
Yeah.
It's always the tricky one.
Yeah.
I guess the pole mode in that case would not really be, it would be perfect, almost lossless.
Yeah.
But yeah, it's a good point you had with this additional layers, and I guess it's the same with the ground conductors and such, which typically when you model it, you just check this check mark in PSCAD and say eliminate everything, which kind of reduces everything and makes it perfect. But for sure, I think that is an important kind of aspect of future work, to see like if you have a proper representation of all the grounding, let's say you have a land cable maybe, because then this continuous grounding might not be applicable. And then you try to simplify it by saying that I only care about this one, and how much kind of difference would you get? I think that would be a very interesting study for sure.
Yeah, indeed, I got some more questions on that when it comes to the modeling, but you're pointing at an important point there. Intuitively, I agree with you that it's well, it's always the ground that is the troublemaker here, and in overhead line based systems, that's a really critical one, and that's where the frequency dependency comes in, and maybe also one of the reasons why it was hard to pick up those schemes in the past. Yeah, you mainly based, if we look a bit at the cable-based systems more in detail, your solutions have been proposed for DC systems, and there is also really a need there, as you pointed out. You can't really wait. That being said, could you also think of using the same methods in AC? Would you say that they can also directly be applied, or do you see issues there for AC cables then?
Yeah, I think in principle, yes, but then you also have, I guess the grounding becomes even more complicated if you have this cross, what do you call them? Transposition of the cabling earthing, so to say, could also be. And I guess also the theory is of course, it's valid for all frequencies. So from that aspect, it should work. But I guess the important part is then if you can measure accurately enough. Because for CVT, for instance, or something, then you will also have some problem with measuring high frequencies. Whereas in HVDC, we're kind of fortunate, let's put it like that, to have a very good measurement equipment. A question I had in general with, and that's also what spurred me to ask for AC cables, was whether you could get internal reflections, because now you have a rather idealized model in PSCAT. There's more going on inside the cables. You already put some challenges with AC there. Do you think that could be an issue in DC or in AC? Yeah, I guess you could technically have it in DC as well. I kind of looked a little bit on this mixed, so to say, if you have a cable and an overhead line, and then you only measure at the end, so to say, and try to solving that by introducing a kind of reflection coefficients and kind of. I think the problem is that if you try to do that, I think it becomes very complicated very quickly. Which then again, reliability and security.
There's always a price to pay, as you pointed out.
Yes.
Because I mean, there's in the modeling, you have an idealized line now that you have. You also had you used the test system. There also an assumption is being made. You also pointed this out in the thesis on the grounding of the sheets and the armoring. What was the assumption there that you used, and how valid is that one, do you say?
Yeah, I think this one was a offshore kind of configuration, I guess so. So I think they were subsea or submarine cables, which I guess then continuous grounding is a more valid assumption, I guess, than for land cables.
Yeah, they typically have a wet construction, and you connect the sheets to the armor here and there, or several intervals, so it's pretty okay.
Yeah, exactly.
But there are still limits to the model. Where would you say this is sitting then in the frequency range, or where would you need more detailed models? Where would you need the actual?
Yeah, that's a good question. I have not really gotten into too much into the modeling part. That was a little bit of a strategy from my side as well, saying that, there's other people who are much better on this than me. So that's kind of what I try to do, and just borrowing this kind of theory. But for sure, I think that this is definitely I think it's probably going to be more for high frequencies though. I mean, if you kind of low pass or something, you can probably live with it anyways. And I guess it also depends on how you set your protection eventually. Because even though this kind of simulation under ideal circumstances gives you 0.000, then, I mean, it's not going to work like that in practice. I think that we can kind of be certain of.
Yeah, you're right. It's really for very high frequencies. If you were to go to the megahertz range and want to look at over voltages on the sheets locally, but that's a different domain, I would say. So we can stay away from that. But I do think that for AC, things would be a bit more challenging,
for sure,
in terms of also internal reflections.
Yes.
Pointed at the transposition of the cables, it's more the cross bonding of the sheets.
Yes, exactly. That's what I meant.
You internal.
Yes.
So I think their work, would be needed. Or the question is whether it could be applied.
I think the advantage of this method is that at least your kind of assumptions are kind of visible, or you can see where they are, rather than just putting a model and simulating two cases and they say, I base my protection on this setting because PSCAD gave me this, which is kind of, then you make an assumption on the cable, but it's not shown, kind of. But yeah, That's good, valid point for sure.
And then on the differential protection principle itself, what I noted is that you kind of use you have two ways in describing in your traveling waves. You can describe them in terms of currents and then have the contribution of voltage coming into the equations via the admittance. Or you could do it the other way around, or you describe it in terms of voltage and then the contribution of the current coming to your characteristic impedance. Now, in older works, it's always the voltage-based representation that has been used. You did it the other way around.
Yeah.
Could you maybe point out why you prefer that that formulation?
I think for the differential current, I mean, it makes more sense that you actually get the current inside the fault, so to say. I think that was the main reason. And then obviously, since the universal line model is based on current sources, then it kind of comes free as well.
Yeah.
So I think that was the reason.
Yeah, I agree on that. Was also what the point I thought was the main reason why you used it, because you have the universal line model implemented in this fashion. Now, yeah, on that I would like to challenge you a bit, because if you look at the way the currents are developing in the fault relatively slowly with respect to the voltages, also if you think about how you're going to protect your DC system with reactors at both sides, it's mainly the voltage waves that would kind of reflect first, right? So would you then not prefer using the voltage based equation? I know mathematically it's the same, right? I mean, it's an equivalent representation.
Yeah, I think I mentioned it in one of the papers, just very briefly, saying that currents gave a higher margin when I tried them, basically. And the reason for that was that during an internal fault, you get this kind of very quick high peak that kind of decays a little bit. But I did not look too much further into that.
Because also there in the text, I think on page 43, you provided an example and you applied an external fault there. And there it's really clear that it's the currents that you see changing in the adjacent lines, because the voltage waves are kind of halted, let's say, by the reactor sitting between that line and what's going outside. But I think if it would have been an internal fault, it would have been more information in the voltage signal that you would get there. And to make my point a bit more clear, my main argument would go like this. If you would say that it's mainly the information is mainly sitting in the voltage, because that's where you see the largest reflections, let's say those are the biggest quantities, then there is less risk in using the voltage and then the current multiplied by an impedance on which you could make faults, than to use the current plus the voltage multiplied by an admittance on which you could make faults, because it's a fitting, right? It's a model based approximation. That would be, let's say, my main reason why I would say that I don't have the results, because you presented one method, which I think is very, very interesting and very good. But if we would use the equivalent representation there, the one based on voltages, it might be more robust from a practical point of view.
Yeah, could be. And I guess another reason was that it kind of fits in quite well with the other one, because then you only need to calculate this convolution one time. But yeah, for sure, definitely. I think that. But I think it has to be evaluated.
Yeah.
But from a practical point of view, could be.
Yeah. And on the threshold based method, so when you did a comparison, there you basically, and it was also shown on the slides, I think it was page 66 and 67 in the thesis, you say, okay, the traveling wave based method gives me the best performance. I also kind of see a lot of the information in the voltage, DC voltage. I would rather bring the point, I see most of the information in the voltage, and it's kind of good enough probably for detecting. I agree that it was a perfect overlap, but on the other hand, you also rely on the model there.
Yeah, that's true. But then again, also if you use a voltage-based only, so to say, then you also rely on the models from PSCAD. It's just you don't see it in the protection, so to say, but the thing that you base your setting on, or how you choose your setting, is still using that very model. But yeah, I think I got the same question actually for this conference actually.
Okay.
He said, but why don't you just use voltage derivative? Yeah, sure. But then again, it's not certain that you have a reactor on that side. It could be that you don't have breaker in that bay, for instance.
Yeah, if you don't have a breaker, you don't have a reactor,
no.
then everything changes.
Yeah, I mean, as long as you, then for sure, I think voltage is very robust, for sure. Mm-hmm. And yeah, I think, yeah, as you said, we saw it in the results. Disconnecting a converter did not really change anyone. It's pretty much the same anyways. Just a small variation.
Yeah, and in the comparison with threshold-based methods, yeah, I'm not sure I completely agree with you. You basically say, okay, one of the challenge with threshold-based methods is they have to be carefully tuned. And you're right, you depend on simulations because you cannot tune them on actual systems. That's a big issue, and that is where the risk is. I agree, that's where the risk is. But then I would bring in the argument, yeah, but if you throw in a model, then you basically shift the risk to the accuracy of the model that you throw in. So my former supervisor called this the law of the conservation of misery. So I think you put it more elegantly, that you say, okay, you can optimize something, but you win here, but you lose at another point. So I would say that's the price to pay then, that you kind of shift the risk to the accuracy of the model. So it doesn't come for free.
No, definitely not. But the advantage could be that maybe the model could be validated at site, more or less. Maybe you could do like a step response of 10 kV or something. And if you validate the model in that, maybe you can have more confidence in the protection, which maybe, I don't know. I think I put that also as future work.
Yeah.
But as long as you know where your kind of assumptions are, I think, as you said, there's nothing for free.
So in terms of using the method, in terms of applicability, I was wondering if you would have very short cables, would it become an issue there?
Yeah, probably. I think then you probably come into all this kind of very high frequency sampling, and but then the question is also, because then the reflections are going to be so quick, so then maybe you can kind of just neglect them and pretend they're not there, and then put a small low pass or
and I was also wondering whether the processing time could kind of become an issue or not, because on that I don't have any idea, but you still have to be able to process things quickly enough to also reach a decision. Or is that not an issue in reality, you think?
Yeah, I mean, I guess it depends a little bit, because I implemented this. And we ran it in, I think it was also demonstrated during SIGRE 2018. Christian was presenting it. Because then we actually tried to implement all of these things just to make sure that it actually works. But yeah, I think what I did was to reduce the models, basically. So the slider in PSCAD where you can set the accuracy, then you can just, I don't care if it's 0.001. For it's not really that. So reducing the order of the fitting will kind of help quite a lot. But otherwise, I think that, I mean, as long as you're running on some kind of specifically designed hardware, some digital signal processor or something that's optimized for these kind of operations, then it should not be a problem, I think.
Yeah, on that aspect, I also had a question. If you were to implement it in reality, how would you go about it? Because nowadays, if you look at traveling wave-based models for real-time applications, more and more vendors, let's say real-time simulation vendors, are moving to FPGA-based implementation. Would you also need dedicated FPGA-based implementation, or can you simplify things by reducing the order of the fitting, like you said? Or is a sacrifice on security on the accuracy that you make too large?
Yeah, that's a good question. I think that you should probably not go to FPGA is the first thing you do.
You can avoid it.
Yes. But I guess that is always a kind of fallback. But I think that for protections, they are, if it's so sensitive that you need these very accurate models, then I think, yeah, you have a problem, I think. So kind of my intention was that maybe 3 or 4, 5, 5th order maybe, maximum.
Yeah.
Just because you can accept some, if you get some differential current, 100 amps or something, maybe that doesn't really matter. I mean,
and it's also the way you tested it with lower order fitting than yes, yeah. Because that brings me to the next point I would like to raise, which is on the validation. And yeah, there I completely agree with you that it's impossible or next to impossible to do a scale down setup in a lab. I'm also not a firm believer of that. But nevertheless, I'm wondering why you choose also the universal line modeling and in the relay and for the validation. What were the main reasons for using that model for testing?
To be honest, I think that it was kind of how it was developed. I think it was, or the idea came from simulations in PSCAD basically. And to be honest, they have been quite good at marketing this model. So it has a very good reputation. But when reading the papers, they also, or when they implemented this universal line, they also said, we have these other models as well, which to me, I mean, they could have been equally as good, probably somewhere in, what do you call it, digital sampling or this SED domain, for instance, and then said, but we want it to be not dependent on time step, for instance. But I mean, if you're implementing something on that has a fixed time step, then you might as well use this first model, I guess.
Because what I would put there as a criticism is that you're essentially testing the working of your relay with an internal model against a model that is the same as what is in the relay. So it's kind of obvious, especially if you would use the same fitting procedure, same accuracy, numerically, etc., that you would get a one-on-one match because you do exactly the same. So in terms of a validation, I felt it was definitely the first thing to do, but in terms of really validating whether it could work, I was wondering if we could not, let's say, have next steps there to be more certain about it.
Yeah, for sure. Yeah, that's a good point. And I think I don't really like the word validation. And I think I wrote that also in the paper. That was more, I think I used the word demonstration or something, just specifically because I did not want to say that, because it is the same thing. So of course, if you put the same parameters in, then you're going to get the same out. So it's more of a sanity check of the implementation than anything else, I guess.
Yeah, because you could as well have used, for instance, the numerical inverse Laplace transform, I think, which should work as well. I mean, if you can keep everything linear, which for these things you can assume, which is not the case for everything you do in PSCAD, but for these particular studies, I mean, maybe that could have been, I don't know whether it would have brought much, but I think it would have been comparison against a model that doesn't necessarily suffer from the same inaccuracies as the one you implemented in the protection. So I was just wondering if it kind of gives us a bit of a blind spot to potential weak points of the algorithm, but
yeah, that's a good point. I think that definitely future work.
And something else, if you go to the cable parameters, I guess you now got them from the analytical functions that PSCAD has internally. So you, I guess you gave in the geometry, material properties.
Yeah, it was a little bit of a reverse engineering, but you get the file with a bunch of numbers in, and then you can pick them out from there, basically.
Because there's also a tendency there in the cable modeling to go and test it with more elaborate models and get the parameters from finite elements.
Yeah. I mean, that could be one way, sure.
But I completely agree with you that just putting it in a real-time simulator is not going to tell us much more, and rather on the contrary. I mean, I think the only thing would be, as you said, the computational kind of. Do you have time to calculate all these things, or will it stall out? Or that's something I was maybe missing a bit in the thesis. As you said, I did it, but I didn't include it. So I think that's I mean, actually, I wrote a paper on it and it was kind of finished, and then something else came up, and I never submitted it.
which is kind of unfortunate, but
that's sometimes how things go in reality.
yes.
If we go a bit further on the modeling, another point that I had there was the fault model. So your fault conditions that you have, they're really idealized. How realistic is this? How would it refer to reality? Because I'm just wondering whether those idealized conditions are maybe a bit too idealized in realistic situations.
Yeah, for sure. Yeah, I guess for the differential protection, it should not really matter that much. I think it's more for this kind of single-ended. So if you get some kind of, I don't know, inductance in the fault loop, and then internal fault with some kind of, so you don't get this perfect step, which is kind of what it relies on. I think you can definitely get some problems for sure. But exactly on how good they are, I think it's hard to say. And to be honest, I don't know even how to test that. I guess you can kind of make some estimation on, I guess, ground path impedance or something. But yeah, and I guess it also depends in reality. I mean, if you have an overhead line, and it's hard to say how well is this tower grounded, for instance. It's yeah, definitely a source of error for sure.
Yeah. But it's one of the questions, like is it good enough? But yeah, probably at those points also the proof of the pudding will be in the eating, I guess. So if we talk about the principle itself and the robustness, I definitely think that the idea you have been presenting is very interesting. But if I challenge you a bit on the robustness of it, as we discussed, you changed. I appreciated the last chapter where you varied the parameters, but I would argue there, well, it's still a universal line model relay tested against the universal line model with varying parameters. So it's a bit more of an open question, and I have to really, and that's rather from an industrial perspective. If you want to use the algorithm and you want to commercialize it, what would be the steps you would say are needed to fully trust it?
I would probably say some kind of cable test for sure. I mean, just to make sure that how accurate these kind of models are. Especially in this kind of frequency range, which is not really that high. I mean, it's fairly low stuff. I think that would be probably the most beneficial, of course. Yeah. But like what you call it, desktop work for sure. I mean, it could be a good idea to try different models and see how they behave. But I guess then it comes down to which model is most accurate. But it could give you a good idea on kind of what kind of sources or magnitude of error you could have potentially.
So that would more be, let's call it a validation, like doing actual tests and see whether it works, or would you do something more with it then?
I think in that case, probably make a measurement on the cable and validate the model itself and not so much on the protection. Because if the model is okay, then the protection should be. And I think that is probably the easiest way of handling it.
Or do you see ways as well to improve the model based on the measurements, or would that be a bit difficult in practice?
You mean some kind of online adaptation or
online or offline?
Yeah. I mean, that could be one way for sure. It could probably be a lot of development work though to get it working, but yeah, I mean, if you can use all the information that you have available somehow to make it better, then yeah. Definitely.
Something I was also wondering about in this regard is the measurements. You didn't really discuss them in the thesis. So I've got a few questions there on the potential influence of the measurements on the algorithm. And to be a bit yeah, provocative here. You compare data from a model with data from almost the same model that you implemented in the relay, and you start from there, and the two are the same. But the question is, in reality, you would kind of have your model that would be fed by data from the measurements. There's a lot of different steps in between. Where do you think the main challenges would be?
Yeah, I actually thought about this as well, and I think the challenge could be to get equal kind of frequency responses of both, because if they are equal, then they kind of cancel out. But
what do you mean from both?
From voltage and current, I guess. So if you have some kind of low pass characteristic of the current, then it's not going to match up, of course. But if you introduce the same one on the voltage, so to say, so you get equal, then it should kind of cancel out each other. So, but exactly how to get them? Yeah, that's a good question. But in general, the HVDC ones are quite, I'd say, high bandwidth.
And is bandwidth enough, would you say, kind of order of magnitude to achieve this type of protection already? Bandwidth, yeah. I was just wondering about the overall requirements it was put on your measurement circuit in terms of accuracy from a static and a dynamic point of view. Sampling, I mean, that's more processing, but
yeah, I think in order of magnitude, I think I used 50 microseconds or something. In one of the papers, I tried to simulate this kind of digital signal processor to get the time, execution time, to make sure that we don't exceed it. But then when I implemented it, it was actually much lower in reality. So I don't know how that model was working.
And you modeled it then in PSCAD directly, or
no, it was just an implementation basically on Texas Instruments simulator. I just want to make sure that all these calculations and actually fit in this 50 micro. But yeah, I don't know.
Yeah, I'm another point you didn't point out. I mean, is calibration at the two ends. Is that something that could be an issue, or how would you go about that in an actual site?
Yeah, I guess the most critical case would be if you don't have DC breakers and don't have any reactors on the sides, and then you get an external fault. So you get a very sharp fault, basically, because then you need to measure both current and voltage very correctly to get this very, very fast wavefront. And I guess that would probably be the most critical one to get everything, because there's a small error on high the IDT or the VDT will kind of have a big penalty, I guess, on the performance.
But would it not be a risk that it's two separate measurement devices as well there? I mean, that's from a practical point of view, where I kind of would see a bit of a challenge, especially if you want to compare the measurement values themselves, or you want to get them in the difference in a certain accuracy band.
Yeah, I mean, yeah, in that case, if you get this very sharp, because as long as you have reactors, kind of, then all the external faults are kind of, I mean, I guess you could have one between the current measurement and the reactor, which kind of would be hard to, but then it doesn't really matter if the protection trips, because it's still kind of on the line side. So maybe you can live with that one. But otherwise, all the external faults are going to have some kind of reactor if you have DC breakers everywhere, I guess. So then you actually limit all the voltages and currents anyways, so they are fairly slow.
And you would argue then that with that main distinction coming from, you can be a bit more relaxed on.
I think so, because I think that if you have individual differences between different devices, or say in the two stations, they should kind of fulfill the same specification, I guess. I guess then you need to make sure that whatever is outside the specifications, let's say, that you get rid of it somehow through some anti-aliasing or some way.
and we're almost at the end of my pages. As you see, I got a bit of an open question here. If you put your work into perspective of current trends, recently a number of commercial devices have entered the market based on traveling wave based protection. Much of the solutions are different, I would say, from what you're proposing. Where would you say are the key differences with how they went about what they call traveling wave-based protection?
I have, to be honest, not read that much of them, but I guess it's mostly Schweizer. They are very keen on this. It seems like all the other manufacturers might be a little bit more old school. But I think there they kind of rely, they only use current or voltage, I think, in general, and then usually measuring some kind of timing or something like that. So in that case, it's fairly different, I would say. Different approach, completely.
Yeah, I would agree. But could it be? I mean, they targeted it for AC systems. Comes with the challenges we just discussed with respect to the measurements. You see big differences there in challenges in measurement, AC versus DC, for the currents and the voltages.
Yeah, I guess if you only measure the time, so to say, and try to get this reflections or something, then I guess you kind of eliminate a lot of uncertainties of the parameters, I guess, because then you only have time, basically. But I don't know exactly how it's going for them. So I saw that I was actually Googling traveling waves this morning just for a slide. And I saw that NCE had also put a paper or a questionnaire, I guess, to the manufacturers regarding if they were using this traveling wave in AC networks. But I didn't read it fully. I I had other stuff to do. But I mean, I think it's definitely interesting, but it seems like a very different concept. And to be honest, I don't know exactly how well tested it has been. I know that they have put some test cases, let's say, out in the field, but yeah,
I agree with you. It's quite different, and it's kind of marked as differential current. So you have all the elements in the title, I would say, but it's also from the limitations of the measurement circuits they're using. It's much lower bandwidth, so they're kind of using parasitics in their measurement circuit to detect spikes and then compare spikes. And but that's not, I mean, then you're not very accurate on the magnitude, right?
No,
that's also
exactly.
why I was wondering whether you can ensure at the DC side that you can get that accuracy to get it working. Because in AC, apparently, I mean, the solutions now out on the market for DC are not allowing it, or they are not based on, say, on such a level of detail.
Yeah.
So if we're going to the end of my questions that I had, what would you say is the main challenge that you see with the methods in implementing it, in getting it working, getting it reliable? Main uncertainty, or
I think you can probably just implement it as it is now, but I think that back to security, reliability. I think I'm most worried about the models, for sure. Like how well can you trust them? And I think that is probably the main problem, I would say.
And the time delay, do you think that's a key issue, or not that much?
Yeah, could be, definitely. Because I mean, we're not really using that kind of fast communication today. But I mean, if you install one fiber, then you might as well install 100. You still have them, and then you can say, but I want one for my protection, and then you have more or less infinite bandwidth. It could be possible to do it, but also I've tried to ask a couple of people also here in KTH, and I'm like, can I just connect whatever to this device, and then so I think that could also be some interesting work for sure.
Because I think the time delay here and really getting things synchronized is probably a key challenge. You also looked into that, I would say, quite in detail in the last chapter. I really like the optimization based approach, but there I was wondering, is it going to be a lot of overhead in terms of computation to get that working in practice?
Yeah, for sure, definitely. And once we implemented it, I kind of found some I'm not going to say weaknesses in that algorithm I put in the paper, because then I basically had an idea to combine. So if you have two cables, then you measure the optimal and then you kind of combine them somehow. But what turned out happening was that if you had a problem with one kind of optimize it and then it kind of switched back all the time, which was obviously not optimal. But yeah, of course, it's going to be overhead for sure. But I mean, I don't know, a couple of tens of micros, I would say.
Yeah. And the fact that you kind of have to buffer the signal, compare it, shift it, and then optimize it, is that going, do you think that will create a delay additionally that is significant? I mean, significant enough to delay the decision, or is that all in all?
Yeah, it's a good point, because I only looked at external faults, and then I think I only mentioned the same thing. It's important that it doesn't disturb an internal, but what could happen is that you shift away basically one of the signals. So if you get one sort of, you see the fault current starting, and then you can kind of shift that away. Definitely, that is definitely a risk.
Yeah, because I was wondering, could you not just, let's say, have a more brute force approach there and just, let's say, buffer the signal and then just shift it by one sample and kind of see when it is close enough and then hook up? Or is there a risk to that you hook up to the wrong one based on the results you had? Or
it's good. Yeah, it's a good point, because I was kind of trying to optimize all, let's say, the first sample as well. So I tried to keep all the peaks. But let's say that you have, because I never kind of put some kind of detection algorithm. So, I mean, in practice, you would need, I don't know, 2 kiloamps for a couple of 100 micro or something. I don't know. And if you have that assumption saying that it's okay to have one spike of 100 micro or something, then of course it could be that you can get a much better or robust kind of optimization, because then you can say, it's fine if I have one, but I'm going to catch up later. So that would, Yeah, as I said, I think that your work is going to spur a lot of new research anyhow, and a lot of ideas that will be developed from it. So I really appreciated reading it. So thank you, Niclas, once again. Thank you for the very interesting text. Very clearly written, I have to say. A lot of attention to detail. Very nice explaining figures and also animations today. So I really enjoyed reading it. Thank you. Thank you.
Chairman, my reviewers.
Thank you very much, Jeff, and thanks, Niclas. Very interesting discussion indeed. I will allow ourselves 7 minutes break. So we reconvene at 11:45, and we will then be picking up with questions from the grading committee. So I suggest we all take this opportunity to stretch legs and perhaps have a sip of water. So, ladies and gentlemen, let's get reconvened and continue. So the next step is that our grading committee is given the opportunity to ask any questions for clarification or make any comments or, well, general on what they've observed and what they've been reading. And we will be doing this part in order of the furthest traveled distance, which I have determined this morning, which means that Professor Stephen Finney from the University of Edinburgh will be starting off. I'll be handing you the mic. So, yeah, I guess. Here if you wish.
Okay, let's see. So firstly, I'd like to congratulate Niclas on a very clearly presented and interesting thesis and presentation. Good. So also Jeff has covered all the good questions. So I've had to very quickly come up with my second-rate questions. Actually, no, not second-rate question. The first thing I'd like to do is to pick up on something Jeff talked about in terms of validation of the traveling wave models. Do you know if there's been any work done matching the type of traveling wave models that you've done against real cable or overhead line installations?
Not publicly, I think. Not for these kind of HVDC kind of length. I know there has been some kind of validation for AC cables.
Right.
I think in Aalborg they had quite a lot of work done. I think. And I have actually tried a little bit, which I've never published, but for headlines to compare some data from site to actually make sure that it kind of works.
Okay.
Both in trying to figure out or finding the models from transient data and also kind of applying them. But yeah, other than that, I don't know if there's too much work.
The other thing I was wondering, and maybe it's a little bit off topic, is once you've got an HVDC system, you've got a connection to the HVDC valves, which might allow you to inject some signals for model identification. Is that something that would be an interesting area to look at?
For sure, definitely. Yeah, that could be done for sure. The question is how far up in frequency you would be able to kind of go, but
potentially to quite high frequencies. You've got, with the multi-level converters, you've got potential to inject signals onto the DC line.
Yeah.
My last question now is related to the DC circuit breaker and the added inductance. So you've picked on a figure of 50 millihenries. Where is that extracted from?
I think that was actually in the model when I kind of got it. But I think it's usually 50 or 100, depending on where you read, I guess.
Oh, okay. And really, do you have a feeling for what sets that? Is that set by the internals of the DC circuit breaker, or is it interaction with the time it takes for the protection to identify the fault and clear?
I guess it's mainly the breaker, and then protection just have to be faster, I guess.
All right. Did you come across in your work any discussion of using proactive breakers to do some current limiting?
No, I have not really looked into much into that, but definitely, I think that is one important aspect when it comes to also reliability. Because if you have some kind of current limitation, then you can take a chance a little bit from the protection side, and then use that additional time to actually make sure that you actually should trip. But yeah, I've not specifically. I tried to avoid the breakers as much as possible.
Fair enough. Okay, that ends my questioning.
Okay, thanks very much. We'll be handing over to Thanks, Stephen. Handing over to you, Anne-Katrin.
Yeah, just give me a chance, right, to do the logistics. Thank you. I guess I'm more invited for the, let's say, more practical questions. Of course, I'm the only one from the group of the three of us who's not from the university. So my question is also, and Jeff almost covered this question, but not exactly. So I'm super happy that you left this question for me. You ask about, okay, how can it be applied to short cables? The cables that we are planning in Germany, that we also talked about in the break. I think for traveling waves, they are like short cables, even if they are 500 or 600 kilometers long, but they are land cables. So we need to have joints every 1.5 or 2 kilometers, which is for traveling waves like a long series of very short cables. What do you think this will have an effect on the things that you did in your thesis?
I mean, for sure, it's gonna, because then you will have reflections, of course. The question is, like, how close do you get if you just try to ignore them, I guess? Because eventually, I mean, looking at end to end, eventually all these kind of junctions will kind of look as a continuous, I guess. But good question for, because I think it's also a bit of a challenge to simulate, I guess, when you start getting to so many. But yeah, that I don't know. But then again, I guess all the cable joints will also be designed, I guess, to minimize the reflections, I would assume, to make sure that you get a good performance. So I guess even during internal faults for the cables itself, is probably important that you don't get any kind of extreme voltages because of strange reflections. But exactly what kind of impedance you would see or how much of a reflection you would get, that I have not looked into.
So, well, for the time being, it's not planned to mesh them in the very first beginning. So maybe it's not that urgent to answer this question. But I think it might be a very interesting case also here to look further into. And another very practical question, which is more aside your thesis, is, and you triggered me in one of your sentences saying, yeah, okay, you know, it's a kind of trade-off between planning and designing a protection scheme. And my question would be, okay, what would be your advice to our system planners when planning an HVDC or MTDC system? What would be your advice? How many circuit breakers or how should be all the single protection zones be designed? Maximum number of meshes, maximum number of lines included, kilometers of length, bus bars. Is there anything that you could advise them?
Yeah, I guess it comes down to, I guess, the cost.
True.
But I mean, from a technical point of view, of course, it's best, the more, the merrier, so to say. Because then you have more flexibility as well. Then, I mean, if you have, I don't know, depending also what kind of breaker you choose, I guess. Because then you can also maybe have something with this proactive, if you have that. And that could then potentially increase the reliability, I guess. Because then you would not be, or the consequences of a call it a wrong decision by some protection. I mean, if you only have a couple of them, if something trips, then you might lose a big section. But if you have many of them, then maybe you just lose a couple of lines, maybe. And specifically, if you have some kind of reconnection scheme, I guess there has been also some propositions on this open grid kind of philosophy, where you basically, it doesn't really matter that much, the first kind of identification of the fault. You just open and then you reconnect. Could also be a way to kind of avoid any problems that potentially could come from having to make the decision too quickly. But yeah, I think it's interesting, but I think the problem is also that it's going to be hard to gain experience, which is kind of what you would like to do, I guess. You would kind of want experience with a smaller systems, but now we are kind of going to the big ones immediately. And I think that is a big risk, because I mean, if you make this investment and buy your breakers, and then you're going to have trips every 2 weeks for just nothing, then of course it's going to lose kind of confidence in the technology. And yeah.
Okay, still a risky area.
Yeah.
But well, I like your way of answers, because it's something that, well, we expect from manufacturers saying, well, it depends on choice.
Yeah.
No, I really enjoyed also reading your thesis, and I also in our break discussions. I highly appreciate the outcome, because I also see the challenge when working in the manufacturer's world and doing a PhD thesis as a hobby. I think it's not an easy thing to do. So congratulations on this.
Oh, thank you.
Even if we don't know whether it's a PhD in the end. So, but
yeah.
So,
Right, I have to stand up again. I understand at this university, a professor is not allowed to sit down while a student is standing up. Okay, I thought it was the other way around, but right, back to academics, and I understood that I have to now decide to the difficult questions to see if you pass or not. Let's go back to the discussion at the end with the opponent about the traveling waves and delay, and let's go back to the original Takagi algorithm. This is actually pretty simple. You look the amount of wave energy coming out on one side, and you subtract what came in on the other side a bit time back. So you measure on the other side, you measure it and very quickly drive it to the other side. Within Germany, you can drive as fast as you want. I think the speed of light is a limit in Germany with cars on motorway. So the moment you see something come out that didn't come in, you have to trip. There is no delay. The only delay would be the difference in speed between the waves on your cable and the waves through the communication link. But cables are pretty slow. So I don't really follow the discussion you had in the end about delay time. Can you not trip immediately?
Yeah, but I guess in that case, it would be more of this kind of permissive scheme, right? Because, or are you sending?
No, I take differential scheme.
Okay.
The Takagi scheme.
Yeah.
You gave me the credit, but it was Takagi.
Okay, yeah. Yeah, because, but you need to wait until you, I mean,
you have to wait until you hear from the other side.
Yeah.
But the other side has an advantage compared to the actual disturbance.
Yeah.
But the disturbance have to travel through that slow cable. While the other side uses a shortcut called a fiber optic link.
Yeah.
It goes with the speed of light, and how fast do waves propagate to a cable? Half the speed of light or something like that.
Yeah.
So it's pretty slow. It's so fast.
Yeah, exactly. And I think in optical fibers, it's, I think 2/3 of speed of light. So definitely it is faster in optical fibers than
right.
The cable.
In other words, you get the information from the other side until before the actual electromagnetic disturbance had the chance to reach you.
Yeah.
If something reaches you faster than it came through your fiber optic, you know, oops, it must have originated on the way, or not.
Yeah, it could be, but then I put this.
Yes or no?
Yes or no? Yeah, I mean, if you have
an academic, I only for the non-academics. As an academic, I only think in terms of yes or no. Anything in between is like, no, we don't want that.
Yeah, if the optical fiber communication is faster, then yes, then there's no wait.
Yeah.
But I was a little bit conservative as well, so I put in this 0.5 millisecond.
I mean, yes, okay. We come about that later with your difficult question. I mean, yes, you're obviously not sure and you wanted some delay, but come back to that later. Okay, a bit of a terminology. In your title, you call it transient line modeling. You talk about traveling wave-based protection. They're basically in modeling 3 domains. There's a steady state, there's a transient state, and a traveling wave-based state. What did you do, transient or traveling wave? It's not steady state, I presume. Where are you located in that one?
I mean, yeah.
Actually, what's the difference between transient and steady state? Oh, sorry. Between transient and traveling wave-based?
Yeah, good question. I don't know. Is there any difference?
Oh, a good answer for you. It's not a good answer. Is there a difference? That's a question to you.
The question to me. To be honest, I don't know anything about a traveling wave kind of domain, which is faster. But I mean, the transient wave, or transient are basically traveling wave models. So I'm not sure if I completely follow the question.
Okay. No, let's not go along this too long. This again, something we can talk about for hours, academics. But, well, actually, I am allowed, but they promised me lunch. Let's go back to something else. As I said before, I did my PhD myself on this subject. a few years ago, and actually I could have used the same title with just one letter difference, AC instead of DC. The work on using traveling wave-based transient line modeling for over at AC lines was very active in the 80s, and in the 90s it died out. There was some work done in China on that where they tried it, but the research on it pretty much disappeared completely. It was both too complicated and not needed. So yeah, not possible, not needed. That combination doesn't really encourage research. And then it popped up again. ABB bought me a beer and took a copy of my thesis. Roughly. What's the difference between AC and DC? Are there any fundamental differences between AC and DC with respect of these kind of protections? And would it be more easy for DC or more difficult for DC?
I would assume it's probably easier for DC, because then you don't need to deal with this kind of transpositions and those kind of things.
That's basically not specifically AC/DC, but the physical structure of the lines.
Yeah, I mean, I guess the theory is the same, so it should not be that much of a difference.
There is actually one big difference between AC and DC from a protection viewpoint. Will every fault in AC generate traveling waves?
Yeah.
Zero crossing?
Yeah, but then again, if you get the fault in the zero crossing, that is also, I don't know how likely or how often you.
It was a big discussion in the 80s actually, and that was
Yeah.
So we never managed to answer the question, but it was a big discussion.
Okay. Yeah, because I mean, you would imagine that it would actually, or the arcing would happen during maximum, or at least.
Well, actually, lightning strokes would occur anywhere, so there is a chance. No, exactly at zero crossing would obviously never happen. We have a few more, I think. Oh yeah, this one here. You mentioned at the conference they said to you, why don't you just use differential, voltage differential for dVdt as a criteria? Right?
Yeah, for this.
Why is that a bad idea? Why is it, generally speaking, a bad idea to use time differential for protection?
You mean this?
Actually, generally, I mean, you use sometimes some delta V, and I understood at the conference somebody told you, why don't you just use your dVdt as a criteria? Why is that generally a bad idea for protection?
I mean, it's exactly what is being used in LCC, HVDC for many years. So there's nothing wrong with it. The problem is that if you don't have reactor.
The fact that something is used for many years does not mean there's nothing wrong with it.
No.
But why is it, generally speaking, something to be very careful of using dVdt for protection?
Yeah, I don't know. I mean, it's perfectly valid protection, I would say.
Oh, yes, certainly, completely valid. But how about noise? Noise will be amplified. High frequency noise will be amplified.
Yeah, but I mean, the detection would be so, or long enough so that noise should not really.
Well, if the protection is long enough, you actually use an integration, an averaging.
Yeah. But I mean, well, I need to be careful not to say too much. But
well, it's a standard balance again. You have to say enough, but the more you say, the higher the chance you say something wrong. So there's an interesting balance there. Back to balances. What you called as the most difficult questions. So let's keep it to the end. This, I mean, dependability, security, unwanted trip, non-trip, fail to trip. You looked at that through looking at forward faults, backward faults. That's internal fault, external fault. But there's more to life than faults. There's a lot of other things as well. And also, there's a third factor in this whole trade-off. It's not just dependability security. There's a third factor. Which one?
That I don't know.
Actually, you mentioned it. You said you have to wait 30 years to know.
Oh, okay.
I mean, now obviously, I guess, I'm not sure. In the Netherlands, they nowadays let fault stand forever. I understood. You saw the films. But by the way, the first time I saw something like that, yeah. There's nobody from the Netherlands here, I hope. But you obviously want it faster than that, a decision. So the third factor is the time to make your decision. If you wait long enough, or better said, the longer you wait, the better you can be the trade-off. You need some kind of trade-off between. How did you do that trade-off? And if you didn't do it, how would one do that trade-off?
Yeah, that's a good question, because I've tried to avoid at all making actually anything or saying anything on the detection part.
You actually say there is no optimal design, which I disagree with. What you mean is there is no perfect design. There is an optimal design.
Yeah. Okay. Yeah. Exactly. But yeah, I guess there is an optimal. But then again, you also need to put some figures on on your probabilities.
How would you do? How would you go further in that? How would you start or continue with making that trade-off to somewhat have a protection relay that you can rely on, that it will trigger fault fast enough, but on the other hand, you can also rely on that it not too often will give an unwanted trip.
Yeah, and I think, yeah, I mean, that is I guess the big problem in general for protection design, because it's so much based on experience than anything else.
You will have to convince first the patent office, or probably first your employer, and then the patent office to actually go further with this. And you don't get the experience before you convinced somebody like 50 Hertz actually buy your relay.
Yeah.
So you have to do something before that.
Yeah, for sure.
How would you do it? How would you start? How would you recommend somebody to do it?
Yeah, I guess then it comes back to a little bit on this kind of, I guess, modeling and so probably trying to approach the problem from any possible direction, I guess.
I mean, you talked about faults, non-faults, forward, backward, forward fault, backward fault, basically. But there are more non-faults than backward faults. What more could there be? Could you make an examples of things which are non-faults, which may still trip the relay?
Yeah, I mean, I guess that is always the danger with, especially transients. So, I mean, there could be many different types of disturbances.
Which one would you start looking at?
I don't know, maybe you have a chopper or something, could be. So you get a very high kind of or a discharge backwards, which then kind of turns off again, which definitely could cause some.
Actually, any switching action.
Yeah.
Any switching action causes it. Any change in the steady state electromagnetic field will cause traveling waves, will cause tensions. Can you give some examples of those?
Yeah, I mean, yeah, sure. You can, I don't know, deblock converter maybe, or I guess you can switch in some line, or take out.
Well, you could model it. You would start with modeling it, because the relay hasn't. You haven't.
Oh yeah.
Convince anybody to start buying the relay. So.
Okay, I thought you meant of actions. Okay, fine. Yeah, definitely.
Okay, the last question is basically anything else you would recommend to move towards a better balance between dependability, security, and operating time?
Yeah, it's very hard to say something in general, of course. But I guess operation time, I mean, I get that is more or less fixed from the breakers. But of course, then, you know, it's not going to be kind of a valid approach to build multi-terminal systems if you don't have reliability, even if the protection is fast enough. But yeah, to be honest, I don't know exactly.
Mr. Chairman, I rest my case.
Many thanks to the grading committee. And now for the really difficult question, the backstabbing ones from friends and colleagues and so on. So the floor is now open for questions from the general public, you are all now representatives of. I'm monitoring the online audience, so if anyone there wants to say something, type something in the Q&A and I will open up the mic. Or if there's anyone in the room that wants to start us off. Of course. I'll pass the mic so that the guys online hear you.
So thank you, Niclas. It was really good presentation and also a really good thesis. I started off a couple of weeks ago trying to read it and realized quickly it takes a lot of time to get in 8 years of knowledge in just 2 weeks. But really this, what I was thinking about is that you mentioned that the most parameter that gives most inaccuracy into the model is the length. And my feeling is that isn't the length the most easy one to get accurate? Or how are we down to millimeter accuracy that we need to have of the cable length, or are we down to kilometers?
It's kilometers, for sure, because I guess what is important or is the time difference, basically, which then is then a product of how quickly your transients are, and I guess the delay, or so definitely it's kilometers.
Okay, yeah, I will not go further than that. Thank you.
Okay, thank you. Any further questions? Nothing online. So let's use a very intentional silence to really make sure that there are no questions. No, the topic seems to be exhausted, and perhaps so are you, Niclas. So many thanks to Niclas, the grading committee, the opponent, of course, and to all of you in the audience. And with this, the public part of the defense is closed. So thanks to us all.